Today we are going to talk about hue and how we control hues in the white LEDs we use for premium architectural lighting fixtures. Let's start by looking at a chromaticity diagram, which we use to chart correlated color temperature, or CCT. Color temperature is measured in degrees Kelvin on a scale from 1,000 to 10,000. In Kelvin, a white light with a lower measure represents a warmer color like a pink or a red, and a higher measure will represent a cooler color like green or blue. When we make our LEDs, we select them from within a two-step macadam ellipse, which means they come from within the same very tight ellipse on the chromaticity diagram, an area where any difference in correlated color temperature is undetectable to the human eye. But we can't just take into account the correlated color temperatures of each LED. We also need to unify the hue. The arced line on this chromaticity diagram represents what is called the blackbody curve, or the Planckian locus of blackbody radiation. This line represents the locus of natural white light, or ideal light, at various times of day. Following the blackbody curve from one end to the other will take you from warmer to cooler color temperatures. But two LEDs can have the same CCT and still have different hues. A close-up of the blackbody curve shows how if you move in a line perpendicular to the curve, the CCT will stay consistent, but the hues will change. These perpendicular lines measure the delta UV value of a given color. Where the perpendicular line intersects the curve, where the delta UV value is 0, you have ideal light. If you move to the positive side of the Planckian locus, or above the curve, the hue becomes more yellow or green. If you move to the negative side, below the curve, those hues will show more pink. Let's look at the measure of an LED with a CCT of 3500 Kelvin. An LED can measure at 3500 Kelvin, but it can fall anywhere along this ISO-CCT line, from the cooler positive range down to a warmer magenta or pinkish negative range. If we know both the CCT and the delta UV value, we can pinpoint that LED on the chromaticity chart. So we use both the CCT and the delta UV measurements to tighten our color binning process, aiming for LEDs that match the center point of a given hue. We used to bin our LEDs consistently below the blackbody curve to avoid any greenish tinge, but after worries about pink hues in some LEDs that binned lower in the scale and improvements in our technology and testing, we have been able to move our target up and tighten it considerably. Our new bin for white LEDs at 2700 Kelvin, for instance, is a very tight range, binned within 0.003 of a delta UV value, from just above to just below the blackbody curve. We should also note here that discrepancies in hue are more noticeable in the lower, warmer Kelvin temperatures. So, for example, for our static white Series 2 and micro ribbon light, we record our CCT temperatures and verify they are within the ranges you can see on this chart. At lower CCTs, you see binning within a range of 30 Kelvin or 40 Kelvin. At higher CCTs, the binning can have a wider range, within 200 Kelvin, because as the LEDs get cooler, the angle of the binning ellipse gets wider, and as it gets wider at brighter color temperatures, it is much more difficult for the human eye to discern a difference, even as it stays consistent with our two-step color binning. We also take into consideration the different circuit types that we use and how to target the binning of an LED based on how driving the LEDs at different wattages and lower amperages can affect their CCT and hue. Finally, we have to account for any LED color shift that can result from the waterproofing process. Waterproofing is done by the human hand, and we have to bin our LEDs based on the effects of thin, impervious layers of silicone. Most silicone will cause the color to shift a little bit cooler, so we track the vector to determine where to bin for our IP65 or IP68 rated products, starting with a slightly lower delta UV value. Binning for those macadam ellipses will start in a lower area, but will shift higher during the waterproofing process to match our original binning for a given CCT. This means that we can confidently state that the LEDs from, say, our IP20 rated 2700 Kelvin static white micro ribbon light will match up to the LEDs in our IP68 rated 2700 Kelvin static white Series 2 ribbon light. Before we ship our products, we check every part of every order. We measure the color rendering index RA number to verify it is above 90, and the CRI R9 number to verify it is above 60, which gives us a CRI of 90 plus. We record the delta UV value and verify it is within a range of about 0.003 on that scale, and we record the X and Y chromaticity coordinates for each project. This can all be digitally tracked in our ordering system, so customers can check any notes when they want to reorder or make additions, and we can check the old coordinates. All this testing means that our LEDs will provide a very pure light for our customers, providing reliable, correlated color temperatures and consistent hues across our product lines.